Okay, hi everyone. So my name is Lucas, one of ACM ICPC's officers. And this week for advanced training, we're going to be learning about sparse tables, which will lead up to lowest common ancestor queries. So if you want the link to the slides, um, you can try this link. Hopefully it works. Yeah, Nikhil also sent it in the chat.
Let me know if you can get access to it. Okay. Yeah, I think it probably works with UCLA email. Do people have access? Yeah, it seems like some people are on it.
Try to access with the UCLA email, but it like I need to request access.
Seems like other people were able to access it with their UCLA email. So I'm not sure what's going on. I can approve your.
Thanks.
I don't know, for me, like when I typed it in, it didn't work, but whenever I clicked the link, it did.
Oh, that's kind of weird. It also doesn't tell me the email that you're requesting with. Yeah, I don't think I can change it to anything less restricted than just UCLA emails. Is it still not working for you guys, or is everything good? Okay, I guess I'll assume it's working, hopefully. Okay. Yeah, well, the link's in the chat, so you can keep trying it out and message one of the officers if it doesn't work. Okay, so first I want to talk about what exactly a sparse table is. So a sparse table is basically a data structure that allows you to do range min and range max queries in like pretty quick time complexity. So you can do like O of 1 querying, and it only requires O of n log n pre-processing. So the central idea is that we're gonna calculate log n values for every index in the array. So I guess like that's one of the reasons why it's called a sparse table, is because instead of storing, perhaps like n values per every index, you're only storing log n. Let's just go through an example to help you better understand like what exactly it's storing. you can sort of see from this image, but here's an example. So let's say we have the following array. And you can see this array has 9 spots with the corresponding values. Let's see if I can write on this. Is writing on Zoom an option? If not, I'm gonna switch to, okay, I'll switch to Notability. So essentially what we have is that, here, let me try to get rid of notifications. Yeah, so let's see. Our array essentially looks like we have 7, 2, 3, 0, 5. Right, so and the goal here is to calculate range mins, okay? So one way to do this is to pre-calculate, for example, all n squared ranges and like pre-calculate their min value, right? So in this case, like you could do that with like n cubed or n squared pre-processing, and then the querying would be O of 1. Another way you could do it is, you do no pre-processing, and when you're asked to query for the min in a range, you just like go through this individual range, and that takes like O of n time. So with sparse tables, like the smart idea is instead of pre-processing all n squared ranges, you only pre-process n log n ranges. And these ranges are specifically like lengths of power of 2. So for example, our sparse table will look like in this case, in the 2 to the power of 0 column. Let's just write all the indices. What is going on? So in the 2 to the power of 0 ranges, the min is easily like determined. It's just the it's just the starting index at that index, or the value at the index. So in this case, it's just the whole array. Hopefully this makes sense so far. And the goal here is to calculate, the min of ranges of length power of 2 that start at each index. So for the first column, this means that we want to find the minimum of ranges of length 2 that start at each of the indices. So in this case, you can clearly see like starting at index 0, the min is 2 of length 0, right? And then also at index 1, we have these 2 values, and the min is still 2. For index 2, we have 0 being the min, and if we just continue to fill this out, we get the mins of length ranges of length 2 starting at each index. So hopefully this makes sense so far. Yeah, I guess like this last range doesn't really have like a length 2, so I guess we can just not put anything there. I mean, that's also an option. So you might be wondering, like, this might be like kind of inefficient if we're like if we calculate the ranges, if we calculate the minimum of these ranges by just going through each range and you know, like keeping track of the minimum. But there's a clever way in how you can calculate each column from the previous column. So for example, for the second column, or yeah, for the column labeled index 2, we're essentially trying to find ranges of length 4, right? Like the minimums of ranges of length 4. But the trick here is that we can use ranges of length 2 to calculate this. And all we have to do is find the minimum of these two ranges of length 2. So in this case, what we look at is we look at the minimum of the range starting at 0, and also the minimum of the range starting at 2. And together, these comprise a range of length 2 squared, starting at length 0, right? So in this case, all we have to look at is these two values. And then these together will give us 0, since, you know, 0 is smaller than 2. And similarly, we can do the same. So, you know, instead of using like 4 times n operations to find the mins of all of these values, we can instead just compare like 2 values each time. And we know that we're going to compare 2 values each time. So when this power of 2 gets bigger and bigger, it still requires the same amount of time, like O of n, to find the minimum. So yeah, I guess we can just continue filling out this. In this case, it's still going to be 0. It's still going to be 0 and 0. Then we get like 3. And okay, I guess like this can be omitted. So another question is like how big of like a power of 2 you should go up to, and obviously like it should go up to log n, or n is the length of the array, because anything beyond that is just going to be, you know, the whole array or beyond that. So in this case, I think it's sufficient to go up to 3 or 4, but we'll go up to 3 in this case. And in this case, it should come out to 0, 0, and then everything else is left empty. So hopefully everyone understands like how this table is computed, right? And like understands why exactly it takes only n log n time to compute these values. So now the question is like, how is this even useful, right? So let's say we had a query that was like, find the min of the range 0 to 7, right? How would you answer this? Well, one way to answer this is we check if it's in our array, right? And in this case, it actually does exist in our array. This should be the exact answer. We'll call this like sparse table. Oh, we'll give it a shorter name. Call it ST. So in this case, the answer is exactly like ST 0, 3, right? Because ST 0, 3 is the minimum of a range of length 8 that starts at 0, which is exactly the range 0 to 7. So in this case, we can easily just query the array and, you know, output 0 pretty easily. So what if the query was like minimum of 0 to 6, right? So obviously this isn't an array because the length is not a power of 2. but it's actually pretty easy to get this answer like 0 to 6. So one way you can do it is you can basically like get the smallest power of 2 that's, that's less than or equal to the length of this range. So the length of this range is 7, right? So this range can actually be like built up or completely covered by the ranges 0 to 3 and 3 to 6, right? And I guess one reason why min is chosen is because the min of two ranges, even if they overlap, is just the min of the overall range. So what we have is that we have min okay, I didn't write that well. So yeah, so you can see from here that it takes at most 2 queries to get any range, because what you can do is you can take like the maximum power of 2, length power of 2 range that fits in this range, and then essentially just try like from both ends and overlap this range. So visually, it looks like a range of length 7, and then we have 2 ranges of length 4 that start at 0 and 3. So when we query for the answer here, all we have to do is look at two different positions. We only have to look at this position, right, and this position as well. So as expected, the answer in this case is, the min of 0 and 0, which is 0, which is correct if you look at the array. Does that make sense? Does that make sense in terms of like how you would answer range min queries and range max queries, which is like pretty much the same?
So in all cases, we should be able to get an answer by examining 2 ranges at most.
Yeah, exactly. And yeah, so like the reason why it's 2 ranges is because, even if one range of a power of 2 doesn't fully represent the query range, we can always get 2 ranges that do represent it. Also, I guess another question that you might have is, how do you find like 4 in this example? Like, how do you find the largest power of 2 that is smaller or less than or equal to the length of this range? So one way is to pre-calculate the answer for all possible lengths. And this is like easily doable. You can just generate like powers of 2 and then store this all in an array where you have like, 7 goes to 4, and like 6 also goes to 4, and so on. So this also can be done with like pre-calculations. So this gets rid of like the log n factor in terms of computing the power of 2 that you might need. So yeah, everything should be like O of 1 essentially when you query. Any more questions? I can make a poll, right? That option. Let's see. Okay, I guess I won't make a poll. I'll just go back to the slides. Yeah, so aside from sparse tables, the other option is, or the other background knowledge that is necessary is depth first search. So hopefully everyone knows what depth first search is. If you've taken like CS 31 or 32, you should know what depth first search is, right? So I guess one additional thing with depth first search that we can cover is keeping track of like in and out time while doing the depth first search. So what exactly do I mean by in and out time? For that, we can just like go through a quick example. Yeah, we'll just use a random graph. So let's do a depth first search on this tree, right? What we have is that we're going to first visit this node, and then we're going to visit this node, and then I'll do it in red. So this is like the first node we visit, then we visit this node, and then 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 this node, right? Or actually, we don't really go back to node 1. I think we just go directly to node 3 if we actually do it recursively. So when we keep track of like in and out time, what essentially means is that like we have like a counter like t that starts at 0, and we basically add to the counter whenever we first initially visit a node. And then we keep track of this counter when we first initially visit this node and exit a node. So in this case, we have t equals 0, right, as the in time at node 1. And then we have t equals 2 when we visit node 2. And when we visit node 4, it's like t equals 2. And when we exit node 4, there's multiple implementations, but one way we can do it is that we can also add to the counter when we exit the node. So let's say when we exit 4, we also increment the counter. So in this case, we have t equals 2 as the in time for this counter, for this node, and t equals 3 for the out time of this node. And if we just continue doing this, like node 5 is just going to be t equals 4 as the in time, and t equals 5 as the out time. And then node 2 is going to have 6 as the out time. And when we get to node 3, it's going to be 7 as the in and 8 as the out. And then finally, we're going to go back to node 1 when we exit it finally, and it should be 9. So observe something about these in and out times, right? We can essentially represent them as like ranges, 0 to 9 in this case, right? 7 to 8 in this case. And like one thing to notice about these ranges is that they're sort of like the time that you spend under this node. And by under, I mean like in its children and like further descendants, right? Because like when you first enter a node, and like until you exit the node, all the time is being spent in the descendants of this node, right? That makes sense, hopefully. So what we can do is once we have these in and out ranges, it's very easy to check if one node is an ancestor of a different node, right? So for example, is 1 an ancestor of 5? Let's say we have this following query. Hopefully, does everyone know what an ancestor is? I think the word is pretty intuitive. It's essentially like a parent or like a parent of a parent and so on. Okay, I'm gonna take that as a yes. So one easy way to check if 1 is an ancestor of 5 is to check these ranges. So in this case, we have 1 with a range of 0 to 9 and 5 with a range of 4 to 5, right? And all you have to check is if the other one range is contained within the other range. So in this case, 5 is completely contained in the range of 1. And because of that, you know it has to be 5 has to be a descendant of 1. So you can see like when nodes are not actually descendants, like if you look at 2 and 3, the ranges are 1 to 6 and 7 to 8. So you can easily check that 2 is not an ancestor of 3 or vice versa. So that's just a little background in terms of checking for ancestors in essentially O of 1 time if you do a DFS in pre-processing. So yeah, so now that we have the background out of the way, we can start talking about like what LCA really is. So LCA, it's a very simple definition. It's essentially like the lowest node that's an ancestor of the 2 nodes that you're querying. So like it's just a query given 2 nodes. You want to return some other node that is furthest down the tree, but still an ancestor of both these nodes. And you'll see why this is useful. Like it might seem kind of weird, like why we want this node, but it is useful. So I guess I can give some examples. The LCA of 4 and 5 in this case is 2. Another common ancestor of 4 and 5 is obviously 1. The LCA of 4 and 3 is 1, right? So just basic examples. Okay, so now that we know all of this, how do we actually find the LCA? Okay, and this is actually going to use like all the background knowledge. So here's a general overview. I don't expect you to fully understand this. So what we do is we create a sparse table that tells us the 2 to the jth parent of each node. So it's like a similar idea to the sparse table I mentioned earlier, but instead of like ranges here, it's just like 2 to the jth parent. So for example, if j equals 0, this just means the direct parent of every single node. And then if j equals 1, it's like the parent of the parent. So how exactly does this tell us anything, or for LCA? Well, if we can check that one node is an ancestor of another node really easily, now, given 2 nodes, we can essentially just binary search for the LCA. Well, okay, in reality, we're going to binary search for the node right under the LCA, but you can essentially think of it as we're going to try out some parents. It could be like 2 to the some power parent of node U, and check if it's an ancestor of V. And if it's an ancestor of V, then we went too far in terms of the power of 2. So let's just like go through an example of what exactly I mean. You didn't have to necessarily understand anything I just said there. Hopefully this example will tell you everything you need to know. So let's say we have, I guess we can just use this simple example here. If we have 1 here, 2, 3, 4 here, and 5 here, right? So first we want to create a sparse table of 2 to the jth power of parents, right? So we have our table here. Set it up. It's pretty easy to find the parent of some node. Like you can just keep track of this when you maybe like do the DFS, right? So in this case, let's say we have all the parents from the DFS. So in this case, we have the parent of 1 is nothing. The parent of 2 is 1. Parent of 3 is 1. Parent of 4 and 5 are both 2, right? So in a similar idea as earlier, we can use this column to compute the next column. So how do we compute the parent of the parent? Well, if we look at the previous column, which is just the parent, we can just take the parent of the parent. And what I mean exactly is that, for example, if we wanted to find the parent of node 4, right? We have the parent of node 4 here. And all we have to do is check the parent of node 2, which is the parent of 4. And this allows us to easily get the parent of the parent in just like, 2 computations. So again, from like both of these, what we get is that we get the parent of node 4, the parent of node 2, which is 1. And like similarly for 5, we also get 1, and the rest of them are basically nothing. As for the number of columns that you might need, you can basically expect it to be around log of the height of the tree. But if you want, you can also make it log n. Like it doesn't hurt to have log n columns when you actually implement it, just because you don't necessarily have to compute the height of the tree. And like it's still n log n overall. So yeah, we can stop here in this case. So essentially now what we have is we have this parent array, which tells us the 2 to the jth parent of every single node in this tree. All right, does that make sense so far? Hopefully. Any questions so far? I guess not. Okay. So to actually find the LCA now, we're essentially going to binary search, right? And the way we binary search, it's like sort of like a binary search, but it's not exactly a binary search. What we're doing is we're going to try out like 2 to the, in this case, we're going to try out 2 to the, maximum log that we have. Let's say we try out 2 squared and like 2 to the 1 and 2 to the 0. So we're going to try out each of these powers of parents, right? And we're going to test if this parent is an ancestor of the other node. So let's say our query is LCA of 4 and 5. Okay. So our first step is going to check if 4 is an ancestor of 5. And again, we can do this really easily if we have like the time in and the time out at each node. All you have to do is check if the range of 5 is completely included in the range of 4. So I'm just going to leave all that all the details out in terms of the exact code you might write, but let's just assume that we have this checker in like O of 1 time. So when we have LCA of 4 and 5, we first check if 4 is an ancestor of 5. So that's going to be a no, right? They're clearly not an ancestor of the other one. So what we can do in this case is okay, I guess a better way. Okay, let's try out. Let's put a node 0 here just to make it easier for implementation. And let's assume we have column index 2. And in this case, they're all going to be zeros because that's like 4 parents above, and we're going to assume we have this like ghost node 0, which exists. And we can set like the time in at this node, like the range here, it can be like -1 and an infinity. Like essentially it's an ancestor of all the nodes, right? Because it's above the root. So this is like all implementation details. It just makes it easier to implement. So what we do is we check is 4 an ancestor of 5. No, right? And then, okay, now the next check we do is we check if the parent, the 2 to the power of 2 parent. So let's call this table like ST again. We're checking node 4 again. And we're checking if the 2 to the power of 2th parent, which is the 4th parent of node 4, we're checking if that's an ancestor of 5. So clearly, like in this case, we're going to get 0. And clearly the answer is going to be yes, right? So what does that tell us, right? It tells us that perhaps we went like too far in like the power of 2, right? We went up too far in the tree. Like 0 is obviously like way too far up. Even if we actually had the LCA, like our goal here is to find the node like right under the LCA. And the reason why we're trying to find the node right under the LCA is because we can't exactly find the LCA because we don't know. Just because something is like an ancestor of something else, we don't know like what exactly is the lowest. So we're trying to find essentially here a node right under the LCA, right? That's a parent of node 4, or it's an ancestor of node 4. So in this case, you can visualize we're like jumping to node 0 here, and we're like, oh, that's too far. So what we can do is that we know that like 2 to the power of 2 is just too big of a jump. So we don't want to use 2 to the power of 2. So we move on. And what we move on to is like 2 to the power of 1, right? So in this case, when we query our table and we check for ancestry, again, we're gonna get an answer of yes, because we have the parent of 4 is 2, and 2 is an ancestor of 5. So again, we're like, okay, this is too far of a jump, right? And then finally, we try out actually 2 to the power of 1 is even higher. It's 1. So again, it's yes. It's like too big of a jump. And then we try out 2 to the power of 0 with 5. And in this case, it still returns yes. So again, it's like too big of a jump. So in the end, our current node is still node 4, right? And all we have to do is just get the parent of node 4, which is also equal to the value stored in column 1 of our sparse table. So essentially, we're trying to like jump as high as we can without it being an ancestor, and we're essentially going to get the node right under the lowest common ancestor when we try all these like jumps, right? And in this case, the answer is the parent of 4, which is 2. Okay, hopefully that makes sense. I'll go through like a better example. This example is a little too easy, I guess. Does anyone have any questions about this example, actually? No? Does it make sense? Yeah, hopefully. If you guys are bored, you guys can take a look at the problem set in Codeforces. Okay, so how about I give a better example? Okay, we'll get a better tree. Let's say we have this tree, right? And our query is, what is the lowest common ancestor of 6 and 10? Wow, Jesus. Okay, so again, we can like compute the sparse table, but I'm just gonna like not do that this time. So what we have is we check if 6 is an ancestor of 10, right? And if that's the case, then we can just return 6, because obviously the lowest common ancestor of 2 nodes where one of them is the ancestor of another one should just be the higher node, which is the ancestor. But in this case, it's not true. So I can just write that down. Nope. So now we're going to try out these powers of 2. So the first power of 2 we're going to try out, let's say we try out 2 squared. So we're going to check if this node is an ancestor of 10. And this node comes out to be, when we have 4 jumps, it's going to be node 0, because that's 1, 2, 3, and then node zeros. And the answer in this case is just going to be yes, and we know that this is too big of a jump. Now we're going to try out the next biggest possible jump, which is 2 to the power of 1. Right, and again, we're going to get yes, because node 2 is an ancestor of node 10. So again, that's like too big of a jump. And then we're going to check two to the power of 0. And in this case, we're going to get no, because 4 is not an ancestor of 10, right? And we're going to set our new current node from 6 to where we jump to, right? In this case, it's going to be equal to 4. And this is going to be our new current node. And then we can just like continue this process. But in this case, there's like no more of the process, because we've done like 2, 1, 0, and there's nothing left. So in this case, our answer is just going to be the parent of 4, which is node 2. Hopefully this process makes sense. I guess like one thing I can clarify on is that you should like continue to update this current node that you're on. And what you're essentially trying to figure out is like the binary representation of how far down this node is from the actual LCA. So in this case, you can see that these like yes, yes, no answers, if we make yes a 0 and no a 1, we're getting the binary value of 0, 0, 1, which is a jump of 1. If, for example, we were trying to find 6 and 3, right? LCA of 6 and 3. What we're gonna get is we're gonna get like yes from 2 to the power of 2. We're also gonna get we're gonna get a no for 2 to the power of 1, and we're also gonna get a yes from 2 to the power of 0. Because when we jump from, because in this case, our node is 6, and our current node becomes the 2 to the first parent of 6, which is node 2. And node 2, if we check the parent of node 2, that's node 1, which is an ancestor of node 3. So again, we're going to get yes here. And the binary representation that we're going to get is 0, 1, 0. And this represents exactly like how many levels it is to be right under the LCA. So you can see here that it takes a jump of 2 to reach right under the LCA. And again, our answer is just going to be like the parent of this final node that we get, which is 2. And that's just going to be node 1. So Tony asked, how did you decide to jump to 2 initially? Yeah. So again, you're just going to start at the largest column in your sparse table, which is going to be at most log n, right? Because you have n nodes, you know that like storing jumps of huge powers is like unnecessary. Like all you need is 2 to the log n as like the maximum jump that you can do. Okay, any other questions that you don't have to ask in voice? You can just type it out in chat potentially. Does everyone understand what's going on? Is there like a poll? I mean, if there aren't any questions, I guess I can move on. Oh. Yeah, we can do a poll too, anonymous voting. All right, open polls. Okay. Yeah, so I think I'm gonna move on. So now, like, how is LCA any useful, right? How does computing this ancestor node like tell us anything? So one way it's useful is actually like in a very standard problem, like computing distance between nodes in a tree, right? Can anyone tell me like some other way you could compute distances between nodes in a tree? Maybe like based on last week's topic. Yeah, so Tony typed Dijkstra, right? That's a pretty good idea. Does anyone know like what the time complexity of Dijkstra might be? Right, like if we have like a tree Let's assume we have n nodes and q queries for distances. Does anyone know like what the time complexity might look like to actually answer all of these q queries?
If you're going to do a new Dijkstra for each one, then that's like qn log n. It's like,
yeah. One way is to, for each query, just run a Dijkstra from one node. And this will tell you the shortest path from that node to every node, which is a little overkill, but it'll tell you, the shortest distance between this node and the other query node. And this time complexity would be essentially q times n log n. Another way is to pre-compute all the shortest distances, perhaps using Dijkstra, and you can do that in n squared log n. And then just like store this all in a matrix, for example. And then you can answer queries in O of 1. However, both of these could be potentially like not good enough, right? Like if n was 10 to the 5 and q was 10 to the 5, then we can do neither of these choices. So instead, we can use LCA. So how exactly do we use LCA? So an important feature of a tree is that there's only one shortest path. And there's only one path in general that doesn't repeat nodes from one node to another node, right? So let's say we want to find the shortest path between this node and this node. What does that look like? Well, it's just going to be this path, right? And I also claim that this path always goes through the lowest common ancestor. Can everyone see why? Like the reason why it passes the lowest common ancestor is because it goes up, right? It goes up until, it doesn't need to go up further than the lowest common ancestor because you can just take a path going down from the lowest common ancestor back down to the other node. Like if you go up further, you're just gonna have to backtrack back to this lowest common ancestor. Right, so essentially computing the distance between two nodes is just computing the distance between each node with the lowest common ancestor and like summing them. And what's nice about this is that the lowest common ancestor is an ancestor of both these nodes. And the distance between a node and its ancestor is just like the difference between their depths, right? Their levels in the tree. So for example, we have 0 here, depth 1 here, and depth 2 here in these three levels. And let's say we're trying to find the LCA between these two nodes here. What we have instead is that we can find the distance between each node with the LCA. And if so we can use LCA to find the LCA. And then if we have a pre-calculated array for like the level of each node, then all we have to do is query this array and just like take differences, right? So in this case, the path length is just going to be 2 minus 0 and 2 minus 0 because it's just the difference in levels, and our answer is going to be 4. So as you can see, like this querying is extremely fast because all it takes is a log n query for the LCA, and the actual computation of like the distance is O of 1 because all you have to do is query for the levels. Yeah, so if you're given n and q both going up to like 10 to the 5, for example, our preprocessing is n log n, and our query time is q log n. So in both these cases, or like with both of these huge bounds, we can still efficiently answer all the queries. Does that make sense? Does anyone have any questions? Does anyone want
This
to
would
go
also
through?
work if you had
Oh.
like weights in the tree, right? Not just if it's just like
Yeah,
everything's one.
yeah, exactly. So distance is just like a simple case. You can actually do weights, because instead of levels, you can just compute, the cumulative weight sum up to each node from the root, and use that instead of the level. Doesn't work for directed graphs, right? I mean, like, you don't really think about trees as directed. I think in this like context, trees are, first of all, they're rooted and like it's undirected edges. Yeah, I don't think a tree is defined with directed graphs. At least in like computer science. Well, okay. I mean, you could, but like, okay, in this context, like a tree just means undirected. Yeah, like Jacob said, like it gets weird. Like you don't really know what's an ancestor of another thing if you have directed edges. Any more questions? So I think usually for intuition, like if you see like paths in a tree, then maybe you should be thinking like LCA. Just because LCA handles paths pretty well in terms of splitting up the path into two paths that are more easily dealt with, because they're both, like vertical paths essentially. So that's just a little bit of intuition. There's honestly not that many LCA problems that you will see. Like they come up occasionally, but not so frequently. Yeah, I don't think there's any questions. So go back to the slides. I think that's it in terms of content. Here's the attendance code. If you want ACM prizes, if you want clout on the membership portal,
What are the prizes?
put in this attendance code. What are the prizes? I don't know.
What did they do last year?
Yeah. I actually got a prize in freshman year, which was 2 years ago, and it was like a Facebook electric backpack, or like solar panel backpack. So, and I think the first place prize was like Google Home, which is maybe not that valuable to some people. I'm not sure exactly what the prizes have been recently though. Yeah, so hopefully everyone understood. Again, there is a problem set in Codeforces. If you're not in the group, message some officer. The problem set is pretty short this week, so I think it's short because there's not that many LCA problems in general. Like I haven't encountered that many. And also like sparse tables are also infrequently used. Like usually you're not going to get a problem that just tells you like to query for like the min of some range directly. So yeah, I don't think there's any any problems that require only like sparse tables. Like I think they're all LCA problems. So if there's no more questions, I'm going to end the recording.